Hello and welcome back. In this video, we'll be introducing the binormal vector and torsion. We'll end up getting a formula for torsion, be able to determine this, and we'll also give the definition for the binormal vector. All right, so let's place this in context of what we've done so far. We have the unit tangent vector, which tells us direction of motion. We also have the principal unit normal vector, which tells us direction of turning. Now, if we're just in two dimensions, these two vectors completely describe the trajectory of an object along a curve. So that's just in two dimensions, we're basically done. But in three dimensions, we have this other way that we can move around. So the idea here, well, I guess to motivate this, to motivate the binormal vector, we'll first introduce this thing called the oscillating plane. Osculate means to kiss, and so the oscillating plane is this plane that sort of kisses the curve as we move along it. The idea is to look at your unit tangent vector and your unit binormal vector, take those two vectors and form a plane, the plane that contains both those vectors, and keep track of this as the object moves in its trajectory. So for this, I'd like to jump to, I think the easiest way for me, or the most helpful thing for me to understand the binormal vector was by comparing the trajectory, just a circular trajectory and a helical trajectory. So let's do that now. So here I have an object moving along a circle, so just a circular trajectory here, and I have the osculating plane pictured. So that's T and N, and we just formed the plane that contains both of those. Now I want you to keep track of this plane as we move around the circle. So while it looks like the plane is moving, it's really not. The plane is infinite, right? It stretches to infinity, and so really everywhere I go, it's the same as the XY plane. It looks like it's moving around. It kind of is if we place it at the point P that we are at on the curve. But really, this osculating plane is the XY plane no matter where we are on the curve, right? It doesn't move. Compare this to a helix. Let me jump to my helix. So compare that to the helix. There's my oscillating plane for the helix. And now keep track of this as we move around. So notice this oscillating plane now is rotating a bit. Right? It's rotating and changing direction as we move along it. So this is, we know the shadow of the helix on the XY plane is a circle, so it has that in common with the circular trajectory. The difference here is the fact that we're moving up and we're sort of twisting out of the oscillating plane. So what this means is there's some non-zero torsion going on, which is causing us to move this oscillating plane, to sort of twist out of it. This is the idea. So what we want to do is we want to keep track of the direction of this plane as we move across the curve. And we have to think back to chapter 13. How do we keep track of the direction of a plane? Excuse me. How do we keep track of the direction of a plane? Well, what we need is a normal vector to the plane. We need a vector that just comes straight out of it at 90 degrees that's orthogonal to the plane, and then we can keep track of that. So that vector we could get, remember that if I do a cross product of two vectors, say T and N, the cross product will be orthogonal to both of those and hence orthogonal to the oscillating plane. So that's what we're going to call B, our unit binormal vector. It's T cross N, and it comes out of the oscillating plane at 90 degrees. And now keep track of B, the direction of the plane as we move around. Notice how it moves. That B vector is not constant. Compare that to the circle. I'll turn on B for this one. So we'll find T cross N here. There's B. And the vector is unchanged as we move around the circle. Remember, the position of the vector doesn't make a difference. It's the same B everywhere. It's just pointing straight up, so it looks like, and this is a unit vector, so it's because T and N are both unit vectors. When I take their cross product, B will be a unit vector. So it's a unit vector, and so it's just pointing in the positive z direction. So this vector B is actually our unit coordinate vector K at all points. We're going to derive that in the video after this one. We'll actually show that this B vector for a circular trajectory is K. It's a constant. So that's the idea. This is constant, and so if I took a derivative of the unit binormal vector, it would be 0 for the circle. And then, right, jumping back to the helix, or remembering the helix, if I take a derivative of B here with respect to my parameter, it'll be non-zero because this thing is changing over the course of time, or changing over the course of the curve, right? So that's what we want to get a hold of, is the derivative of this unit binormal vector. And that's related to torsion. All right, so let me jump back to this. We're going to actually do some calculations. So that's the osculating plane. We want to keep track of how that moves, the direction of it, and that's the unit binormal vectors, the direction of this osculating plane. B is normal to it. Again, like I said, because T and N are both unit vectors, B will also be a unit vector, right? Magnitude of B is magnitude of T times magnitude of N times sine of the angle between them, right? Remember that definition. And the angle between these two, right, T and N are orthogonal to each other, so that's 90 degrees, right? So theta between these two is 90 degrees, and so sine of that is 1, and so I just get T times N, and like I said, because they're both unit vectors, we just get 1. So B is also a unit vector. So we have these 3 unit vectors, the unit tangent telling us direction of motion, unit normal vector telling us the direction of turning, and now finally this unit binormal vector, which is telling us the direction of the osculating plane. And as I mentioned, if we study the derivative of the unit binormal vector with respect to arc length, say, or time, this relates to the twisting out of the osculating plane, and that's what torsion is. So how do we actually calculate torsion? Okay, so we're gonna use some geometric facts here to get a hold of this. It's a pretty cool derivation for it. So we have that B, our unit binormal vector, is T cross N, and we're saying torsion is somehow related to dB ds, or rather torsion is, we'll say it's related to dB ds for right now. And so that means we're taking a derivative of a cross product, T cross N. Remember, these are not just constant vectors. These vectors change their vector valued functions. So I can take a derivative with respect to the arc length parameter. Okay, so we can use our cross product rule for derivatives. Derivative of a cross product is derivative of the first. So this is going to be dt ds cross the second. Remember the order, careful with the order with this, plus the first, t, cross the derivative of the second, dn ds. All right, so here I can now make an observation. I have to remember how all these different things relate to each other in order to see this, but one of these two terms is the zero vector. In particular, dt ds, remember that's the derivative of the unit tangent vector, and remember that's how we got a hold of the unit normal vector, right? In particular, the unit normal vector was defined to be or we showed it was 1 over curvature times dt ds, right? So that means n and dt ds, like I said, this is a very geometric argument. N and dt ds are parallel. And remember, if you have two parallel vectors and you take their cross product, you end up with 0. So n cross dt ds is the 0 vector. So that means this whole term here goes to the 0 vector. It's just 0 at all points t. Right, this is true for all times t, or all points along the curve S. And so what we get here is just t cross dn ds. So what this tells me is that, so conclusion is that dB ds is orthogonal to t, and orthogonal to dn ds. So remember, right, the result of a cross product, the vector that comes out of this has to be orthogonal to both vectors that I put into it. So it's orthogonal to t and dn ds. So db ds is orthogonal to t and dn ds. In particular, it's orthogonal to t. Now, remember another fact, that if I have a vector-valued function whose magnitude is constant, then its derivative is orthogonal to the original vector-valued function. Now, b, right, we talked about how b, magnitude of b is 1 at all times. So at all points around the curve S. So db ds, being the derivative of a vector-valued function with constant magnitude, is orthogonal to b. Okay, so I'm going to highlight these two things. db ds is orthogonal to t, our unit tangent vector, and it's orthogonal to b. And so there's really, because b and t are orthogonal to each other by how we defined b, that means there's really only one direction that db ds can lie along. And that must be this third vector, the unit normal vector. So from these two facts, we get that db ds is parallel to n, our unit normal vector. So the change in the binormal vector is always parallel to the unit normal vector, which means db ds is a scalar multiple of n. So db ds must be some scalar times n. Now here's a little bit of a weird part. So it's some scalar times n, so we could say tau times n. But conventionally, how we define torsion, right, that's what this t is for, is torsion, we actually use the negative here. So we say db ds is some scalar multiple of n, typically it points in the other direction as n, and so we put this negative here. And then tau is torsion. So the idea is we need to figure out what scalar multiple of n is db ds, and then the negative of that is torsion. And this is, again, convention, why we put this negative here. I know it's a little bit weird at first, but that's the idea. So how do we actually get a hold of a formula for torsion? Right? This is a nice definition for what torsion is. This is a definition for torsion. How do we actually get a formula for torsion? Well, for this, there's a really clever way I can get a hold of this. I'm going to take a dot product of both sides of this with n. So, right, so I have db ds. Let me make sure everything's in the frame. I have db ds is negative torsion scaling unit normal vector n. If I take a dot product on both sides, so db ds dot the unit normal vector, that's going to be minus tau scaling n dot the unit normal vector. And now here I have n dot n. And remember that magnitude of n, it's a unit vector, it's 1. And also remember that n dot n, this is true for any vector, if I dot it with itself, we've used this fact a couple times, it gives me magnitude squared. So in the case of a unit vector, when I take a dot product with itself, I just end up with 1. So n dot n here is 1, and so I just get minus tau out. So that is, so here's my formula for minus tau, db ds dot n equals negative tau. Or if I want, I can throw this negative on the other side and say tau is negative db ds dot n. So in order to calculate torsion, we're going to be finding this db ds, taking a derivative, and dot producting it with the unit normal vector. So we'll need to find a few things to get a hold of torsion. It's not an easy calculation because we need to get a hold of these things, and that takes a little bit of work. But nevertheless, here's a really nice formula for torsion. In the next video, we will apply this formula to both the circle and to the helix and better understand how those things differ from each other and how they relate to torsion. I'll see you there.